Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. This week in astronomy, doubt cast on alien life hints from distant planet, primordial black holes and moons lost magnetism. Doubt cast on alien life hints from distant planet. Last month, astronomers announced what seemed to be the most promising evidence yet of alien life on a distant planet, sparking excitement and hope that humanity might finally be on the verge of discovering we are not alone in the universe. The focus of this excitement was the exoplanet K2-18b, located 124 light-years away in the Leo constellation. This planet is considered potentially habitable because it orbits its star at just the right distance to allow liquid water to exist on its surface. Using the powerful James Webb Space Telescope, a team of astronomers led by Cambridge University's Nitya Madhusudhan reported the detection of chemical signatures, specifically dimethyl sulfide, DMS, and dimethyl disulfide, DMDS, in the planet's atmosphere. On Earth, these chemicals are produced only by living organisms such as marine algae, which makes them potential biosignatures, or signs of life. Although the researchers were careful not to claim they had found definitive proof of alien life, they did highlight the intriguing possibility that life-related chemistry might be at work on K2-18b. Their findings had reached a 3 sigma level of statistical significance, meaning there was still a small but notable chance, about 3 in 1,000, that the result was a random fluke. Since then, however, the initial excitement has been tempered by skepticism. Several recent studies have reanalyzed the same data and found that the evidence for these biosignatures may not be nearly as strong as originally thought. One such analysis was led by Luis Wellbanks of Arizona State University and Matthew Nixon of the University of Maryland, both of whom had previously worked with Madhusudhan. Their review used different statistical methods and expanded the range of possible chemicals from 20 to 90. More than 50 of those chemicals fit the signal from the planet's atmosphere, which suggested that the original interpretation might have been too narrow. Wellbanks questioned the value of a detection that could point to almost anything, asking whether anything meaningful was truly detected at all. He clarified that the new analysis does not rule out the presence of DMS on K2-18b, but that more data is needed before drawing conclusions. The debate over the findings has become part of a larger conversation about scientific method and rigor. Madhusudhan welcomed the scrutiny, insisting that open discussion and challenge are vital to the progress of science. His team has responded by publishing a new preprint study, expanding their chemical analysis to include 650 different compounds. Interestingly, while DMS remained among the top 3 possible chemicals, DMDS, the other molecule central to the initial announcement, was no longer present in the updated analysis. The 2 new candidate chemicals, diethyl sulfide and methyl acrylonitrile, are less known and may not be realistic components for an exoplanetary atmosphere, especially since methyl acrylonitrile is toxic. This shift in findings, despite no new data or new modeling tools, led Wellbanks to criticize the inconsistency in the original team's approach, noting that their entire analysis had changed within a month without any fresh observational input. Meanwhile, other researchers have joined the conversation. A paper led by Raphael Luque from the University of Chicago, which combined Webb telescope observations in both near-infrared and mid-infrared light, also concluded that there was no statistically significant evidence for DMS or DMDS on K2-18b. Similarly, a simpler analysis by Oxford astrophysicist Jake Taylor found no strong signs of biosignatures. Madhusudhan dismissed Taylor's findings, arguing that they failed to account for the complexities of how physical processes influence what telescopes detect. Despite the criticisms, Madhusudan remains confident in his research and expects that more data from the James Webb Space Telescope over the coming year will clarify the situation further. Even if DMS is eventually confirmed on K2-18b, it still wouldn't automatically prove the existence of alien life. DMS has been detected in lifeless environments, such as certain asteroids, showing that the presence of a single chemical is not enough to make a definitive claim. Nevertheless, many scientists remain optimistic that with continued advances in telescope technology and data analysis, the discovery of alien life, if it exists, may be within reach. Wellbanks expressed this cautiously optimistic outlook, saying that this is the closest science has ever come to such a breakthrough. Nixon added, however, that progress must be made carefully and within the established frameworks of scientific methodology, emphasizing that jumping to conclusions, as he believes happened in this case, undermines the credibility of such an extraordinary search. Primordial black holes, a gravitational key to dark matter. Among the many proposed candidates for cold dark matter, such as sterile neutrinos, axions, and weakly interacting massive particles, primordial black holes, or PBHs, stand out as a compelling possibility. These hypothetical black holes are thought to have formed from extraordinarily dense concentrations of matter in the chaotic, high-energy moments immediately following the Big Bang. Unlike the black holes born from collapsing stars, PBHs would originate from subatomic fluctuations in the universe's earliest instance, making them fundamentally different and cosmologically significant. Classically, PBHs are stable, but in 1975, Stephen Hawking revealed that black holes aren't completely black. Through a quantum mechanical process now known as Hawking radiation, black holes emit radiation much like blackbodies, slowly losing mass in the process. This evaporation gives black holes a finite lifetime, and according to Hawking's calculations, only those with initial masses greater than 1 trillion kilograms would have survived the 13.8 billion years since the birth of the universe. Yet Hawking's framework was semi-classical and didn't fully incorporate quantum gravitational effects. In recent years, new theoretical developments have emerged that challenge the assumption that smaller PBHs should have already evaporated. A particularly intriguing idea is the so-called memory burden effect, introduced by the physicist Gia Dvali in 2018. In this framework, a black hole is not merely an empty, consuming singularity but rather a condensate of gravitons, the theoretical particles that mediate gravity. These graviton states carry vast amounts of information, and as the black hole emits radiation and shrinks, the burden of this stored information intensifies, stabilizing the black hole and slowing or even halting further evaporation. Essentially, a black hole becomes a prisoner of its own memory. This shift in perspective means that primordial black holes once believed to have evaporated could, under the influence of memory burden, still exist today as undetectable, non-luminous mass, cold dark matter in its most elusive form. This insight has led researchers in Japan to propose a method for detecting such memory burden PBHs by studying the gravitational waves generated by the same early universe curvature perturbations that formed them. The team, led by Kazunori Kori from the National Astronomical Observatory of Japan, argues that although we have not detected dark matter through particle accelerators, underground detectors, or space telescopes, it might not be made of exotic particles at all. Instead, it could be macroscopic in nature, composed of stable, ancient black holes. As experimental attempts to detect dark matter continue to yield no direct results, the prospect of purely gravitational dark matter becomes more plausible and more urgent to investigate. The physics underpinning the memory burden effect suggests that Hawking radiation is significantly suppressed in these PBHs, due to the immense entropy each black hole contains. A typical stellar mass black hole has an entropy on the order of 10, in units of Boltzmann's constant, dwarfing the Sun's entropy, which is around 10. Because the rate of Hawking radiation might decrease according to some power of this entropy, the resulting lifetimes of even small PBHs could be vastly longer than previously thought. Consequently, PBHs with masses as low as 100 kilograms and as high as 10 million kilograms may still be lurking in the cosmos, invisible yet gravitationally influential. One promising production mechanism for PBHs involves regions of the early universe with extreme spacetime curvature fluctuations. These would have gravitationally collapsed into black holes during the radiation-dominated epoch, and the same curvature spikes that caused their formation would also have generated gravitational waves. These gravitational waves, traveling through the expanding universe, carry unique spectral fingerprints directly tied to the mass of the PBHs they were born alongside. By calculating how these waves would have redshifted over cosmic time, Corey and his collaborators were able to predict the frequencies and intensities of the waves that we might detect today. The results of their calculations indicate that memory-burdened PBHs could produce gravitational waves at relatively low frequencies, frequencies that fall into the detection range of next-generation gravitational wave observatories. Instruments such as LISA, the Laser Interferometer Space Antenna, DESIGO, the Decihertz Interferometer Gravitational Wave Observatory, and the proposed Big Bang Observer by the European Space Agency are being designed with the sensitivity to potentially detect these signals. The team created detailed models of the expected gravitational wave spectra and calculated the signal-to-noise ratios that future observatories might achieve after just 1 year of operation. These projections provide not only a theoretical foundation but also practical guidance for designing experiments to test the PBH dark matter hypothesis. In their publication in Physical Review D, the researchers also proposed concrete criteria for how to confirm or rule out the memory-burdened PBH scenario based on observational data. They emphasized that while nonlinear dynamics in the evolution of PBHs will determine the precise shape of the gravitational wave signal, there is a characteristic feature in the spectrum, an infrared tail, that hints at detectability within realistic instrument constraints. Although peak frequencies might be as high as 30 MHz, far beyond the current reach of LIGO and similar facilities, the redshifted portions of these signals could be picked up by new observatories like the Cosmic Explorer, which will vastly extend the sensitivity range of terrestrial interferometers through longer arms and improved technologies. Ultimately, if memory-burdened PBHs are the source of dark matter, then the universe's earliest quantum fluctuations and their gravitational wave echoes may finally provide the key to one of the deepest mysteries in physics. Corey and his co-authors believe that embracing the memory burden effect could offer a highly constrained, predictive framework that requires relatively few assumptions. While it's still unknown exactly how memory-stabilized black holes behave at the end of their lives, whether they decay into lumps, fizzle out in gravitational wave bursts, or linger indefinitely, the possibility that the dark matter problem has a macroscopic, gravitational origin rather than a microscopic, particle-based one represents a profound shift in our understanding of the cosmos. The theoretical tools are now in place. It may be that the next generation of gravitational wave observatories will bring the observational confirmation we've been waiting for. How a giant impact sparked the Moon's lost magnetism. For decades, scientists have been puzzled by the mysterious magnetism of the Moon. While lunar rocks collected by astronauts and measured by orbiting spacecraft display signs of strong magnetization, the Moon today has no detectable global magnetic field. This raised a long-standing question: where did the Moon's magnetism go? Researchers at MIT may have finally provided a compelling answer through a new theoretical model that involves a combination of two forces: a faint magnetic field generated internally by the Moon billions of years ago and the intense effects of a colossal asteroid impact. According to their simulations, in the Moon's ancient past, a dynamo in its molten core may have generated a weak magnetic field, far less powerful than Earth's. On its own, this weak field would have left only modest traces in the lunar rocks. However, when a massive object such as an asteroid slammed into the Moon's surface, the impact could have released an enormous cloud of plasma, vaporizing surface material and sending ionized particles flowing across the Moon. This cloud of plasma would not have simply dissipated. Instead, some of it would have streamed around the lunar surface and concentrated at the point directly opposite the site of the impact. When that happened, the localized influx of plasma may have interacted with the Moon's weak magnetic field in just the right way to momentarily amplify it, creating a temporary magnetic spike on the far side of the Moon. If rocks were present in that area during the brief moment of magnetic intensification, they could have been magnetized permanently, recording a field far stronger than what the Moon's core could sustain on its own. This theory helps explain a puzzling observation. Some of the most magnetized lunar rocks are located near the Moon's south pole on the far side, directly opposite one of the Moon's largest and oldest impact basins, the Imbrium Basin, located on the near side. The new hypothesis suggests that the asteroid that created Imbrium could have launched the sequence of events that magnetized rocks on the opposite side. In simulating this scenario, the researchers assumed the Moon once had a dynamo-driven magnetic field of about 1 microtesla, around 50 times weaker than Earth's current field. They then modeled a massive impact and the resulting flow of plasma, using computer codes developed by collaborators at institutions including Curtin University and the University of Michigan. The simulations showed that the plasma would wrap around the Moon and focus at the far side, compressing and strengthening the ambient magnetic field. This process would happen quickly, within about 40 minutes, but it could have been enough to magnetize rocks in the region, especially when combined with another phenomenon triggered by the impact, a seismic pressure wave. The researchers proposed that the seismic shock from such a massive collision would ripple through the Moon and converge at the opposite side, jostling the electrons within the rocks at precisely the moment when the magnetic field reached its peak. These electrons, when disturbed, tend to realign with external magnetic fields, and as they settled back into position, they would have retained a memory of the brief but intense magnetic pulse. The result would be rocks that carry a permanent record of magnetism far stronger than the Moon's weak dynamo could provide alone. This new understanding bridges two previous competing theories, one attributing lunar magnetism to an internal dynamo, and the other to massive impacts. Rather than choosing between them, the MIT researchers argue that both mechanisms likely played a role, and that their interaction holds the key to the Moon's magnetic puzzle. The hypothesis is also testable. Future lunar missions, especially those targeting the Moon's far side near the South Pole, could examine rocks directly for signs of shock effects and remnant magnetism. Such investigations are within reach, especially with planned missions like NASA's Artemis program preparing to explore exactly those regions. By blending insights from planetary science, plasma physics, and geophysics, the team has crafted a cohesive and elegant explanation for a mystery that has intrigued scientists since the Apollo era. Their work suggests that even brief events in a planet's history, if timed just right and powered by immense forces, can leave long-lasting marks in the geological record.